Okay, when we do inequalities, we sometimes have things called conjunctions and some things called disjunctions. A conjunction would be something like something that has and in it. For instance, we'll look at number 5. You have y is greater than or equal to -1 and y is greater than or equal to 3. Sometimes looking at the number line can help you see what the solution to this is. As a matter of fact, that's what I would do if you don't see what the answer is just by looking at the problem. So let's say you get a number line, and you got -1 and you got 3 up here. And we know that y can be greater than or equal to -1. I'm going to do that shading in yellow. Okay, here's -1, and it's got to be bigger than that. And at the same time, it's got to be bigger than 3. So I'll do that in red. Here's 3. We're going to color it in because it's got that equal sign under the inequality. And y greater than or equal to 3 is here. Since it has an and in it, I only want where the solutions overlap because both of these things have to be true at the same time. And that means the solutions are all right here. That's where we see both the red and the yellow. So my solution would just be y greater than or equal to 3. So that's called a conjunction. Conjunction, junction, y'all know that song? What's my function? Okay. There's another junction, okay? So a disjunction would be like number 7. Number 7 says t greater than 0 or t is less than 2. Okay, for this one, we want one or the other to be true. They don't have to be true at the same time. Again, this is called a disjunction. Sometimes graphing this is the easiest way to see what's going on. Let's say there's 0 and there's 2, and I'll do them in different colors. So for the first one, t greater than 0, I'm not going to count 0 as a solution point, but I want things bigger than 0. So that would shade out this way. And remember that's how we show that. Now if I want t is less than 2, here's 2. I'm going to circle it, but I'm not going to color it in. And then less than would be to the left, so I'd shade this way, and it goes on forever and ever this direction. Well, if either one of these can be true, do you see that the whole number line is covered here? So basically my answer here is all real numbers because the whole number line ended up being shaded in. It's kind of hard to see if you don't draw the graph of it. We'll look at number 13. 2z minus 1 is less than or equal to 5, or 3z, and that's a z, it doesn't look like it. I'll try to make it look more like a z, minus 5 greater than 10. Alright, first of all, before I can figure out what the solutions are, I have to solve each one of these inequalities for z, so we'll do that. The first one, we would say to get z by itself, we would add 1 to both sides. And you get, we have 2z less than or equal to 6. And then in order to get the z by itself now, I could say, oh, it's multiplied by 2, so I could divide both sides by 2. And I would have z less than or equal to 6. I'll go ahead and draw my number line. Actually, I'm going to wait. That way I can see what this other number is going to be so I can see where I need to put the 6 on the number line. Okay, so let me go to the other one. I'll graph this z less than or equal to 6 in a minute, but let me see what my numbers end up looking like over here. Alright, I want to get z by itself. So just like when I'm solving an equation, I'm going to add 5. The only thing different about inequalities, if you remember, is that if you ever divide or multiply by a negative number, you reverse the direction of the inequality sign. And we didn't have that going on in either one of these problems. Alright, so I have 3z, after I subtract 5 from each side, is greater than 15. And then in order to get the z by itself, I could say it's multiplied by 3. The opposite of multiplying by 3 is dividing by 3. And so I end up with z is greater than 5. 15 over 3 is 5. Okay, so I kind of know now I need a 5 and I need a 6. Now, either one of these or the other one can be true. They don't have to be true at the same time, so I'm not looking for overlapping here. I'm looking for where the solutions could be, because anywhere we've got shaded on the number line is going to be a solution. So I see that I've got this boundary value of 6, and because there's a line under the inequality, I'm going to color it in. And z less than or equal to 6 means it's going all this way, one to the left. Okay, and then on the z greater than 5, 5 is a boundary. If I were just graphing this inequality by itself, I wouldn't shade in the 5. It actually is covered by the z less than or equal to 6, though, if you notice. So it is going to get counted, even though it doesn't say that over here, where I just circled it in green. Z greater than 5 would be this direction. And it was an or. Oh my goodness, I see that I made a mistake. So if you were confused why I said z less than or equal to 6, you were right. It should have been 6 over 2. That should be a 3 right there. So this makes my number line incorrect. I was kind of wondering, because I've got the book open and I can actually see the answer, so that's how I caught it. I forgot to divide this here. Okay, so let me go regraph that. Let me scribble that out. Okay. And I'll do it in the original blue and green colors that I used on each separate inequality. Okay, so if I got my number line drawn, I needed a 3 and a 5. Alright, so sorry about that if you got confused. It's just, forgot to divide. So I've got z less than or equal to 3. So let me shade that one in blue, since that was the original color I used for this first inequality. So I would say 3 is my boundary point, not 6. I would shade it in. And I would go to the left, because it's less than. Okay. And then if I were over here on the second side where I've worked in green, and I shade that in green, z greater than 5, I would circle 5. It's a boundary value, but I'm not going to shade it in because there is no line underneath the inequality to say equal to. So z bigger than 5 would mean shade to the right, but do not shade in that dot. So that's a graph of what my answers would look like, but my actual answers are up here. They are actually, and I'll circle them in purple just so that you can know what I'm talking about. Right here and right here, these are my answers. And that's what the book gave you. It did tell you to graph the solution set, but and so actually I guess this graph down here is also part of the solution. You were supposed to graph it, so there were two things there going on. Okay, number 17 is another one of those conjunctions where you've got and what we're going to look for is where does the solution set overlap, and sometimes that's easiest seen by graphing, and they tell you to graph also. So here we go. We need to take each equation separately, or inequality separate. It's called an equation when there's an equal. It's called an inequality when there's a greater than, less than. So let me start over here and solve for the one that I wrote first. 2t plus 7 is greater than or equal to 13. Now I kind of had to scribble out this sign because it just didn't pick up with the stylus. When I tried to correct it, it made a mess. So when I'm solving, remember the first thing I do is add or subtract, and I always do the opposite thing. So I'm going to subtract 7 from both sides here. So these would cancel out or add up to 0, and 2t is greater than or equal to 13 minus 7 is 6. All right, I got to get t by itself. It's multiplied by 2. The opposite of multiplying by 2 would be dividing by 2, and I get t is greater than or equal to 3 there. Okay, so I'll graph that in a minute. Let me go ahead over here to the right and solve. I'll use green. That way we can see where each graph ends up on the number line and tell them apart a little easier. If I want to get t by itself here, I could always remember PEMDAS backwards. We add or subtract first. We divide second, okay? So I'm going to do the opposite of a minus 4. That would be an add 4 to both sides. And I cancel that out, and I get 5t is less than 10. And I'm still trying to get the t by itself. Well, t is multiplied by 5. The opposite of multiplying by 5 is dividing by 5. So I'd get t is less than 2. Okay, so let's go graph these on the number line, because we have to see where both of these things are true. So my solution is not these two separate things here. It's whatever happens, wherever they happen to overlap, okay? So I know I need 2 on my number line and I need 3 on my number line because they're my boundary points. So let me graph t is greater than or equal to 3 first. Here's 3. There's a line under the inequality with the 3, so I'm going to shade it in. And t is greater than means I shade to the right. Okay, so let me do the green one now. You may already can see what's happening without the graph, but you're supposed to graph it anyway. T is less than 2, so 2 is my boundary point for the green set of inequalities. And less than means shade to the left. Is there anywhere on this whole number line these two things overlap? No, they don't overlap at all. And remember, the way I'd know they overlapped is if I saw both colors in a certain area of the number line. So there are no solutions here, and how we write that normally and how you're going to see your book give the answer, you can write no solutions, but this means no solutions. This means the empty set. It means if you were to write a set of your solutions, you would have nothing in it because there are no solutions. Even another way to say that would have been, you could have put like these braces with nothing in it, but honestly people don't do that. Even if they do that, they put like that inside of it just to show nothing in there. So the braces are kind of a little redundant. So people usually just use this notation right here to show there are no answers. And again, remember, lazy mathematicians, they want a symbol to say a lot of things so they don't have to write so much. And again, that's just working efficiently. So that's just the empty set. You would probably want to get used to doing that.